As we've discussed earlier, every aggregate should have a root entity, the entity which is the main for this aggregate and which can be referenced by entities and value objects in other aggregates. It's a good idea to create an aggregate root base class, just as we did with entities and value objects. The aggregate root base class usually has three goals. The first one is to explicitly show the boundaries of the aggregates in your domain model. By inheriting an entity from the aggregate root base class, you make it easier to read your codebase and see which entities are roots of their own aggregates and which are just parts of existing ones. Secondly, if you employ optimistic locking, you need to somehow version the entire aggregate. The best way to implement such versioning is to put a version property to the aggregate root, like this. And finally, the aggregate root base class is a perfect place to hold domain events that happened to an aggregate during its lifetime. We will dive into this topic in much more detail in the future modules. For now, I leave the base class empty. We will extend it later on. Note that if you don't need to implement optimistic locking and you don't use domain events in your codebase, it might be just fine to omit the use of this base class, as it doesn't provide much value in such situations. If this is the case for your project, try to weigh the pros and cons and decide whether you want to introduce the additional base class to your domain model or you can get away without it. In our project, we will need it for holding domain events, but it might be not the case in your situation. Let's look at our codebase in the light of what we know about aggregates. First of all, we know that the snack machine and snack entities are the roots of their own aggregates, so let's mark them appropriately. I changed the class they inherit from to aggregate root. Good. There are two other flaws in our code, namely in this particular property. Do you see them? Try to pause the video and think a minute. Unpause it back when you are ready to compare our answers. Alright, so the first drawback here is that we expose the collection to the outside world. The client code can easily add new elements to the collection and thus corrupt the internal state of the aggregate. Namely, the addition of a new slot here would violate the invariant stating that the snack machine can have only 3 slots in it. The second shortcoming is more subtle. The problem here is that we expose the slot entity itself. As I mentioned earlier, it is a good idea to keep the entities that are not aggregate roots inside the boundaries of their aggregates and not show them to other aggregates. It's not always possible to avoid such exposure, of course, but it is in our case, as you will see in a minute. A solution here is to just make the collection protected and hide it from the client code completely. You can see our test doesn't compile anymore because it cannot access the slot collection. To overcome the problem, we could create a method that returns a number of snacks in a particular slot, for example, get quantity of snacks in slot and compare it to the expected value. This design decision entails other problems, however. If we need to get not only the quantity of the snacks inside a slot, but also the snack itself and its price, we would need to create two other methods, get snack in slot and get price in slot, and use them to fetch different pieces of information about the slots. The issue here is that if we need to get a list of all snacks in all slots, those methods would be pretty cumbersome to use. So how can we overcome this problem? As we discussed before, if our code is hard to use or looks awkward, that is a strong sign we miss some important abstraction. Let's look at the slot class again. Do you see an abstraction here that we can extract out of this class? It turns out there is one. These three properties, snack, quantity, and price, are always used together, so we can extract them into a separate value object. It makes a lot of sense if you consider the usage scenarios for them in our domain model. In most cases, we want to work with these three elements together. For example, when we display a snack on the interface, we need to know not only what the snack that is, but also its price and the remaining quantity. So let's create a separate class for this new abstraction. We can call it snack pile. It will represent a pile of snacks a particular slot contains. This would be a value object, so we can make it sealed, because the requirements in Hibernate imposes regarding virtual members apply to entities only. I'm creating a placeholder for the two equality members. We'll write the actual implementation for them in a second. Alright, so now we can move these three properties here, make them non-virtual, and also remove the setters because our value object will be immutable. Creating a parameterless constructor, and also a constructor that accepts all three members. Now we can implement the equals_core and getHashCode core methods. Perfect. We need to add the newly created value object to the slot entity and also update its constructor. Here we can just initialize the snack pile with empty values and remove the snack, quantity and price parameters altogether. The snack machine class has stopped compiling at this point. Let's see how we can fix it. First of all, the loadSnacks method doesn't have to accept three separate parameters anymore. We can replace them with a single snack pile instance and assign that instance to the appropriate slot inside the entity. I need to make the setter for the property public. Good. The constructor of the snack machine class can also be simplified. We no longer need to pass any parameters other than snack machine itself and the position of the slot. And finally, we have an error here when trying to decrease the number of remaining snacks by 1. The first decision that might come to mind is to write such code and just make the quantity field mutable. However, it is not the best solution. Remember, it's a good idea to adhere to the immutability principle and don't mutate value objects. A better option in this situation is to create a separate method in the value object class, subtract1. It would create a new value object with the same parameters as in the existing one except the quantity value. So let's implement it. We just need to return a new snack pile with the same snack. The quantity would be decreased by 1, and the price is also the same as in the existing value object instance. Perfect. The last thing we need to update is the unit test, creating a snack pile to load into the machine. And instead of these three methods, we can create a method that returns a snack pile from a particular slot, searching for a slot and returning its property. Good. Now we can retrieve a snack pile and check that the quantity in it equals the expected value. And I remove this code. Very good, the code compiles and the test is passing now. Let's implement a couple of additional refactorings for our domain classes. First of all, we need to make this public method virtual so that Hibernate wouldn't complain about it. Secondly, we use this line of code for several times in different methods, so it's a good idea to extract it into a separate method. I call this method getSlot and copy the line to it. Now we can use it here and also here. Perfect. The last thing you might have noticed is that we don't actually make any validations in the snack pile value object. It's possible for us to create a pile with a negative quantity or a negative price, which are invalid values for our domain. Let's fix that. If the quantity or price is less than 0, then we throw an exception. Also note that as we use the decimal type for the prices in our domain model, we can potentially set a price to a value that is less than 1 cent but is still positive. We need to handle such situations as well and don't allow prices that are more precise than 1 cent. We just cannot handle such prices with physical money our snack machines operate. So if the remainder of the price after dividing it by 100 is more than 0, then we also throw an exception. Note that it's a good idea to cover these three invalid cases with unit tests. I'll leave it as an exercise. Let's recap what we've done in the previous demo. First of all, we created a fully encapsulated aggregate, snack machine, that doesn't expose its internals to other aggregates. Not only do we hide the collection of the slots, but we also keep the internal entity, the slot entity, inside the aggregate and don't expose it to the outside world. It's a good practice to try to achieve such degree of isolation. In our case, we were able to implement it by introducing a new value object, snack pile. Unlike entities, value objects are perfectly fine to pass between aggregates. Note how we resolved an awkwardness in the code by adding a new abstraction. Always search for hidden abstractions in your codebase. It might be that your domain model can be simplified greatly if you introduce one. And again, unlike entities, value objects are lightweight, and it's always a good idea to move as much domain logic to them as possible. In our case, we transferred almost all responsibilities the slot entity had to the snack pile value object. The slot class now acts just as a host for that value object, nothing more. Also note that we adhere to the immutability rule for value objects. Instead of making the quantity property in the snack pile value object mutable, we introduced a separate method that creates a new instance of that value object.